Hello and welcome to the session. Operating Systems LO2 understand memory and I/O management techniques used by modern operating systems. How do modern operating systems manage memory and I/O efficiently? This video explores key techniques in memory and I/O management that ensure smooth operation and resource sharing. Discover how these systems maintain stability and performance. Logical address space is the view of memory from the perspective of a process. Physical address space is the actual RAM addresses. Dynamic relocation helps map logical addresses to physical ones. This separation aids in process isolation. It enhances security and efficient memory use. Contiguous block allocation can lead to fragmentation. Paging divides memory into fixed-size pages to prevent this. Page tables map pages to frames in physical memory. Fitting strategies optimize space usage. These methods ensure efficient memory allocation. Static loading involves loading the entire program into memory at once. Dynamic loading brings parts of a program into memory as needed. This reduces initial memory usage. It allows for more efficient resource management. Both methods have their own advantages and drawbacks. Swapping moves inactive processes to disk to free up RAM. Virtual memory uses disk space to extend RAM capacity. It allows running larger programs than physical memory permits. This technique is crucial for multitasking. It ensures processes have necessary memory resources. Device drivers enable communication between the OS and hardware. They translate OS commands into hardware instructions. Types include user mode and kernel drivers. Virtual drivers also play a role. Drivers ensure hardware compatibility and functionality. File systems manage data storage and retrieval. Common types include FAT32, NTFS, and ext4. Key features are journaling and file permissions. They also handle file operations like reading and writing. Caching strategies are crucial for performance. Paging divides memory into pages and frames. It allows non-contiguous memory allocation. This prevents external fragmentation. Page tables map logical pages to physical frames. It's a fundamental technique in modern OS. Segmentation divides memory into logical units. Each segment has a name and length. It reflects the program's structure. Segmentation provides modularity and protection. It can suffer from external fragmentation. Virtual memory uses disk space as an extension of RAM. It allows more applications to run simultaneously. Programs operate as if there's more physical memory. Swap space is used for inactive data. It's essential for multitasking and system stability. Fixed loading loads the entire program into memory at once. Dynamic loading loads parts of a program as needed. Fixed loading is simpler but less efficient. Dynamic loading reduces memory usage. Both have specific use cases and benefits. Fixed linking includes all library code in the executable. Dynamic linking references external libraries at runtime. Fixed linking increases executable size. Dynamic linking reduces memory and disk space usage. It also simplifies updates and promotes code reuse. I/O management controls OS interactions with hardware. Device drivers are key components. Interrupt handling allows devices to signal the CPU. Buffering smooths speed differences between devices. Spooling manages data queues for single-task devices. File systems differ in performance and features. FAT32 is simple and widely supported. NTFS offers security and large file support. exFAT combines compatibility with larger file handling. Each system has specific pros and cons. APFS is optimized for SSDs and offers encryption. HFS Plus supports journaling and compression. APFS is used in modern Apple devices. HFS Plus is now deprecated in favor of APFS. Both have unique features catering to Apple systems. X3 and X4 are stable Linux file systems. X4 supports larger files and journaling. BTRFS offers advanced features like snapshots. It's still maturing but provides dynamic resizing. These systems are ideal for Linux environments. Single contiguous allocation assigns memory to one process. It's simple but inefficient. No multitasking is possible. Memory is wasted if not fully utilized. It's suitable for simple embedded systems. Fixed partitioning divides memory into fixed sizes. Each partition holds one process. Dynamic partitioning creates partitions based on need. Fixed partitioning leads to internal fragmentation. Dynamic partitioning reduces internal but causes external fragmentation. Slab allocation is used by OS kernels for small objects. It organizes memory into slabs containing multiple objects. This reduces fragmentation and improves performance. It's efficient for frequent small allocations. It's crucial for kernel memory management. Device drivers translate OS commands into hardware instructions. They ensure compatibility and functionality. Drivers manage data flow and command execution. They handle hardware interrupts for timely responses. Without drivers, OS cannot communicate with hardware. Paging eliminates external fragmentation. It supports virtual memory systems. Paging simplifies memory allocation. However, it requires page tables and can cause overhead. Internal fragmentation may waste some space. In conclusion, understanding memory and input-output management techniques is essential for explaining how modern operating systems operate efficiently. Memory management techniques, such as paging, segmentation, and virtual memory ensure optimal use of system resources, while I/O management coordinates communication between hardware devices and the operating system. These techniques support system performance, reliability, and multitasking. Understanding how memory and I/O are managed enables effective system configuration and performance optimization. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 074843616888.